Here is a paradox almost nobody in the AI hype cycle is talking about. Every modern AI accelerator chip built on a 3 nanometer process needs roughly 30% of its die area for circuits that have not actually shrunk in 20 years. They are still designed by hand, by a tiny population of engineers whose training takes a decade and whose intuition cannot be transferred to software. These circuits are what get the digital part of the chip to talk to the rest of the world, the clocks that the entire chip's logic synchronizes to, the high-speed transceivers that move data on and off the die at 100 gigabits per second per lane, the voltage regulators that turn a noisy power rail into a quiet one, the reference voltages that keep everything stable across temperature. They are analog. They are mixed signal. And on a 3 nanometer node, where transistors are smaller and noisier than anywhere in history, they are actually harder to build than they were at 7 nanometers or at 28. This is what mixed signal engineering is in 2027. The work, the bottleneck, and the two layers of the supply chain that profit the most from the fact that nobody has figured out how to automate it. The mixed signal engineer is the person who designs the analog circuits that make a digital chip useful, not the logic, the interfaces, the clocks, the power conditioning, the data connections. On a modern AI accelerator, 4 blocks dominate the mixed signal engineer's job. Wall 1 is the phase-locked loop, the single circuit that takes a 100 megahertz crystal reference from outside the chip and multiplies it up to the 4 or 5 gigahertz clock the digital cores run on, with less than 1/10 of a picosecond of jitter. Wall 2 is the SerDes, the high-speed transceiver that moves data off the chip at 100 or 224 gigabits per second per lane across a printed circuit board that is electrically noisy and physically chaotic. Wall 3 is the analog to digital and digital to analog converters, the bridge between continuous voltage levels and binary numbers. Wall 4 is the LDO regulator and the bandgap reference, the circuits that hand the rest of the chip a power rail that does not move when 10 billion transistors switch simultaneously next door. Each is a place where AI tools help with layout, but cannot finish the design. Walk through them in order. Wall 1 is the phase lock loop, the PLL. Every digital block on a modern AI chip is clocked. The clock has to come from somewhere. The somewhere is a tiny PLL circuit on the corner of the die, which takes the 100 megahertz reference oscillator from the system board and multiplies it up to the 4.5 or 5 gigahertz the digital cores need. The hard part is jitter, the picosecond level wobble in when each clock edge actually arrives. The specification on a modern accelerator is below 1/10 of a picosecond, root mean square. That is parts per trillion stability at 5 gigahertz, below the thermal noise floor of the silicon itself. The mixed signal engineer designs the loop filter, sizes the charge pump, places the voltage-controlled oscillator, and routes every supply pin so power noise does not leak into the timing. Synopsys and Cadence ship simulators that model the loop dynamics. What they do not do is decide what to do when post-silicon characterization shows the PLL is hitting jitter spec at room temperature, but missing it by 20% at minus 40 degrees Celsius. That is an analog intuition decision. Move the loop bandwidth, adjust the bias, cut a metal mask eco. A senior mixed signal engineer makes the call. There are not enough of them. Wall 2 is the SerDes, the high-speed transceiver block that gets data off the chip. A modern AI accelerator can have 100 or more SerDes lanes on its perimeter, each running at 112 or 224 gigabits per second. NVLink, PCIe Gen 6 and 7, CXL, HBM PHY optical interfaces. The speeds are extraordinary. At 224 gigabits, the signal on the printed circuit board has a wavelength of roughly 3 millimeters. Every via, every bend in the trace, every connector pin becomes a microwave reflection. The SerDes circuit has to receive a signal that has been mauled by 10 centimeters of copper trace and reconstruct the original bit pattern with one error in 10 to the 15th bits. The receive path includes a continuous time linear equalizer to flatten the channel response, a decision feedback equalizer to cancel residual echoes, a feed-forward equalizer to handle precursor distortion, and a clock and data recovery loop to lock on to whatever clock the transmitter sent. Per lane power is in the 100 milliwatts range. 100 lanes is 10 or 15 watts of pure analog. The mixed signal engineer signs off on each block. The signal integrity engineer signs off on the channel. The two sign-off documents are different. Both are required. Neither is a tool output. Wall 3 is data conversion, the analog to digital and digital to analog converters, ADCs and DAREs. They live in two places on a modern AI accelerator. First, embedded inside the SerDes receivers, where the most advanced receive architectures sample the incoming signal, 8 or 12 bits at 100 gigasamples per second, and do the equalization in the digital domain. That single ADC is a circuit at the absolute limit of what a 3-nanometer transistor can do. Second, embedded throughout the chip as voltage and temperature monitors, sampling the supply rails and thermal sensors for the on-die regulation loop. The specifications are brutal. Integral nonlinearity below 1/2 of a least significant bit, spurious free dynamic range above 50 decibels, power consumption budgeted to single milliwatts. The mixed signal engineer designs each ADC core, characterizes mismatch across the converter array, and decides how to calibrate offset and gain drift across temperature. The Synopsys analog FinFET toolkit and Cadence Virtuoso can lay out the geometry. They cannot decide whether the converter should use a flash topology that is fast but burns power, or a successive approximation topology that is slow but efficient for this specific lane on this specific product at this specific node. That is a power versus speed call. The engineer makes it, ships it, lives with it. Wall 4 is the clean power rail, the LDO regulator, and the bandgap reference. When 10 billion digital transistors switch simultaneously next door, the local power supply voltage sags and bounces. The sensitive analog circuits on the same die cannot tolerate that noise. A SerDes that sees a 10 millivolt supply blip will increase its bit error rate by orders of magnitude. The mixed signal engineer designs low dropout regulators that take a noisy rail from the package and output a clean local rail to the sensitive blocks. The LDO has to dissipate hundreds of milliamperes, settle within nanoseconds of a load transient, and reject power supply noise across a frequency band from kilohertz to gigahertz. The bandgap reference is the absolute voltage anchor for everything else, a circuit that produces 1.2 volts regardless of temperature, regardless of process corner, regardless of supply voltage. The fundamental analog primitive that every other regulator and converter on the chip is built on top of. There is no software design tool that produces a bandgap reference at 3 nanometers automatically. There is a senior engineer with a notebook full of techniques learned across 20 programs. There are a few hundred such engineers in the world. The industry is short. So why does analog stay so hard while AI tools sweep the rest of the chip design world? And which two layers profit most from the bottleneck? 3 reasons. Reason 1. Analog does not shrink. At 3 nanometers, the digital logic is faster and denser than ever before. The analog circuits on the same die have lost ground. Transistor noise is worse. Signal swing is smaller. Parasitic mismatch between supposedly identical transistors is larger. A SerDes that took 6 months to design at 7 nanometers now takes 9 months at 3. There is no software fix. The physics moved against analog. Reason 2, the skills are tacit. Mixed signal design intuition lives in heads, not in books or in tool flows. A senior analog engineer with 20 years of experience can size a transistor, place a capacitor, and route a sensitive signal with judgment that nobody's been able to encode into an EDA tool. The current generation of senior engineers is retiring. The pipeline of replacements is thin. Universities graduate 1 mixed signal PhD for every 20 digital ones. Reason 3. The yield versus spec trade is judgment. Every analog circuit has a Pareto frontier between performance and yield. Tighten the spec, and yield falls. Loosen it, and the system fails downstream. The engineer who decides where on the frontier to operate has to understand the system, the customer, the foundry corner data, and the contract. So who profits? 2 layers. Layer 1 is the SerDes intellectual property oligopoly. Synopsys and Cadence each ship cell-by-cell IP libraries for high-speed transceivers. Alphawave Semi is a pure-play independent IP vendor running roughly 15% share. Together, those three companies license the high-speed PHY into every advanced AI accelerator that ships, because nobody can afford to design SerDes in-house anymore. Layer 2 is TSMC's specialty analog and radio frequency processes. N3RF, N5X, the only foundry running cutting-edge analog at advanced nodes, premium pricing, no second source. That is mixed signal engineering, the corner of the chip industry where physics, intuition, and a shrinking pool of senior engineers still decide whether the next generation of AI accelerators ships on time. Real Silicon Jobs is the series on the engineering roles AI cannot replace. Subscribe to see the rest. Next episode goes inside the yield engineer, the role that decides how many die per wafer actually make it past final test, and why a single 0.1% yield improvement is worth $50 million on a high-volume program. Watch the numbers.